Let me know if my screen is visible, the presentation is visible.
Yeah, visible.
Okay, so my name is Anantha Vijay. I'm a software engineer at Vistion. I work in the automotive industry. Like I just joined in the company. So we'll start with automotive security. The reason for this taking this topic in the presentation is because this is cybersecurity awareness month, October. So and automotive security is not well known in the industry. And I'll start. First, I will do a little bit of cryptography. That is just the basics alone, and then I will start the automotive security part because there will be cryptography involved in automotive security. So the two basic schemes in cryptography are symmetric key and asymmetric key. Symmetric key is using one key for both encryption and decryption, and asymmetric key is using two keys. So the problem with symmetric key is if I want to decrypt any data that you give, I need to know the key. Both people should know the same key. The key distribution is the problem here. You can't just send it via WhatsApp or something. It is a little bit hard to share the key. There are some strategies for key sharing problem, but I won't discuss this here. Discuss that here. In asymmetric key, you encrypt using the public key, and the receiver can decrypt using their private key. This uses two key, so the public can be known by everyone, so there won't be any problem. And private key, only the receiver will know. And the next scheme is signature scheme. Signature is to know if the message is actually sent by the receiver. So we don't know who sends the message. We have to verify if you send the message to me. And again, you have two ways here. One is symmetric. This is not actually a signature in case of symmetric. It is called a MAC, message authentication codes. So what you need to know is the key is bound to the message. So if you send, you will append the MAC to the message and send it to me, and I can use the key and calculate the MAC over the message and see if it's equal. And with asymmetric, it is the reverse of encryption. So instead of encrypting using the public key, you encrypt using private key. And let's say I send a message, I will encrypt it using my private key, and anyone can verify that the message is signed by me because using the public key, since it's publicly available. So with that being said, I'll start the automotive security. So nowadays, modern cars are very complex. You're not just driving a car, you're driving a computer that happens to have wheels and steerings. So you get all the features. And it is not manual anymore. Everything is software defined, and you have a lot of computers inside the car. So the automotive security started to become viral or well known after the 2015 GPAC. This was demonstrated by two security researchers who were able to take control of the car remotely and turn off the engine. This was the first, not the first, but the one that became well known and started the automotive security path. Before this, people didn't care about whether the car has security or not. And if a car is hacked, you have a lot of problems. Like if the car is stolen, it will have an impact on the money. If a car is hacked and you can make it crash, then a person's life. So any kind of an impact in the car will have a very big impact on the people's life as well. So cars are very complex. So I'll tell you, there are different ways it is becoming complex. The first one is suppliers. So let's say car is, let's take an example of a Mahindra car. The car is not only made by Mahindra. Only a part of the car will be made by Mahindra. The others will be provided by the tier 1 suppliers. And there are a lot of components in the car, and each will be given by a supplier, tier 1 suppliers. The Mahindra will just be an integrator of and standards and compliances in automotive security. You won't know if everyone follows that. So anywhere you have a flaw, it becomes critical. The next start that I got somewhere from the internet, but modern high-end cars have 100 million lines of code in it. So anywhere there can be bugs anywhere. A number of lines when the complexity increases, security becomes critical, and it will be easy to find flaws inside it. It will be easy to miss things. In the modern end and the Facebook. So Facebook has around 60 line, and the modern end high-end car has 100 million lines. And the ECUs. So the computers that are inside the car are called ECUs. They are embedded systems and a microcontroller unit. There are around 50 to 60 microcontroller units inside the car. Each has its own purpose, and they will do only one thing. So things are faster here. So let's say you have brake ECU. When you press the brake, it has to immediately brake. So the brake ECU is specifically for that purpose. It will take care only that purpose. And yeah, each ECU is an embedded system, so there is many operations being performed on them. Next one, so here is a comparison. So you have the left one is the tire pressure management system that is very small, and the right one is an infotainment system that is the entertainment unit that you have in the car. It's a full-blown computer. It runs Android Auto nowadays. So you have mobile security comes in. You again, it also has it opens up multiple windows to connectivity, and okay. Next one is the networks. So inside the car, you have multiple networks. It's not just one. So if you take your phone, you might have one or two. That is Wi-Fi and cellular. But in a car, you have multiple networks, and each is being used for. First one is CAN. CAN is the most common one that is car. So this of 1 Mbps. We'll discuss about in the upcoming. Others are used only particularly. Next one is LIN. LIN is low cost, very cheap. You don't want the speed. So like the secondary issues, you will have LIN with connected with LIN. Then you have most. Most is the media operating for media purpose, multimedia purpose to stream. It provides 150 Mbps per second, and it is optical fiber. Then you have FlexRay. FlexRay is similar like a high performance scan, 10 Mbps, but it is expensive. And Ethernet, you have Ethernet for diagnostics and much more activities. So CAN is the most common one, and it is cheap, and it has some properties that are useful in the car. So next one is connectivity. So you have a lot of connectivity there with GPS, internet, and everything. Along with that, you have vehicle-to-vehicle communication. That is, you can communicate from a car to a car. That is, let's say you do there are two cars going, and the front car is going to brake. The front car can say to the back car that it's going to brake, so it can take some measures. Then you have vehicle to infrastructures. These infrastructures can be the car manufacturers backend server. Then vehicle to anything. So it can connect to anything like the traffic lights you have and other things. So this also increases the complexity of the car and the product cycle. Most car will take from the design phase to the release phase. It takes around 5 to 6 years, right? Car when you start making the software, when you release it, it might become outdated. The standards might become different and everything. And nowadays, the product cycle has been shorter, and it becomes a problem here as well. So now, nowadays, Chinese market has more share in the automotive industry, and you might know BYD cars and all. They perform better. They do release faster. That's why. So now, what happened was this but we don't have that much capacity to work, right? So the number of bugs increases. So all they think is but some bugs cannot be fixed by software update. When there is a hardware defect, when there's a defect in the hardware, you can't fix it via software update, like the OnePlus green line issue. And the problem that comes with this, the manufacturer has to recall the cars. Recall in the sense they have to take the cars to their service station and then re-affected. So Tesla has a lot of recalls here. So this is just two snippets that happened recently, and it recalled a lot of cars. This takes a loss on the manufacturing side. So when you take automotive security, the first thing that you do is threat analysis, and in automotive security, it is called TARA, TARA, threat analysis and risk assessment. And the first thing that you do is find the entry vectors, that is the attack surfaces. So here we have a lot of connectivity. So like we have GPS, software updates is one big thing. So you can just, if a software update is not secure, you can overwrite the code and get code. Then you have two multiple entries. One is the USB port, Wi-Fi, Bluetooth, cellular. With USB, you get physical access, and you have Android apps. You have tire pressure management system. OBD port is something that is used for diagnostics. That also we'll talk about later in a detailed way in this presentation. Then you have RKE. RKE is the remote with which you can unlock the car by pushing a button in the key fob. This is susceptible to many attacks, which we'll see now. See, the keyless entry system allows the driver to lock, unlock, and sometimes start the vehicle without physically inserting a key. So this is what we get nowadays. That is, you can unlock by pressing the unlock button in the key fob. And there are two types here. One is the remote keyless entry and the passive keyless entry. The one that you is the remote keyless entry system. This so how this works is this is a when you press unlock, you send a code to the car through the radio frequency saying it to unlock. So how does it know if there are two approaches? One is the static codes, that is you keep the code fixed for each car and the fob. The problem with this is let's take a scenario like this. So when you press unlock button, it is through radio frequency. Anyone can capture it. If I capture it, I can replay it again after some time to unlock get 0. And this was very popular, and the cars were stolen. A lot of cars have been stolen using this attack. I think Mr. Robot also has seen with this attack. The next approach is rolling codes. Rolling codes is you change the code after every successful attempt or unsuccessful attempt. This is similar to your OTP. So OTP, you have through an algorithm, you will generate multiple codes and you iterate through it. So the problem, this is also susceptible to an attack called rolling jam. So the attack scenario is like this. So when you press the unlock button on a key fob, the attacker can record the key, jam it as well. So when he jams, the first unlock button press X1 will not go through to the car. Now when you do this, so it didn't work. So now you will try again, obviously. So next, when you press the unlock button again, the attacker can jam that as well and record it. So now he has recorded two things. Now, when you press the second time unlock, unlimit, but then he would send the first one to the car, first code, which will unlock the car. Now the next code will be the X2 that he has already recorded. So after you drive and you come and park it in the space, you lock the car. Now attacker can use the recorded X2 to unlock. So the way that it can be, okay, we'll talk about the next. So the next system approach is the passive keyless entry. This is like when you go near to the car, it will get unlocked. that is passive keyless entry, and this works in the flow. The flow is like this: the car will send a low frequency wake with the channel. This works on a channel response protocol. Car will send a frequency to the key fob, which has a nonce. Nonce is a random number that is used only once. If it detects if the key fob detects it, it will wake, and it will do something with the nonce, and it will send it. The car will then verify the response and see, and if it gets verified, then it will know that the key fob is near, and it can go for the unlock. So this is a challenge response protocol, which works by saying that you have the password but without revealing the password. So you do some operation. So the operation here is MAC, an example operation. So the secret is shared between the car and the fob. So you have secret, and when the car sends the nonce, the key fob computes the secret, the nonce with using the secret key, and transmits the response. Then the car will take the message and do the MAC and verify the nonce. If it's valid, it grants access. This is also susceptible to an attack called a relay attack, but this is much harder to perform. So you have two attackers here. One is one nearby the car. The other one is nearby the fob. So the car will send a chance to the nearby place. So attacker can relay it to the attacker B. Attacker B will relay it to the key fob. Then you will get the response from the key fob for the nonce, for the challenge. Then it will come to attacker B. Attacker B will relay it to attacker A, and attacker A will relay to car, which will unlock the car, and they can steal the car. So this is a relay attack, but this is much harder in real life to do. And the keyless entry systems can be prevented by using the MAC, the remote keyless, and the passive. With passive, you can have a time. So let's say you send the challenge at 1 second. If the key fob is nearby, you will obviously know that it will come within the next second. But since the relay attack is on a longer path, it will take time to come. So you can invalidate the nonce that you get, the response that you get. So, and the most used signal network is CAN in the car. So this was released in 1986 by Bosch. It has only 2 ways. That is the main advantage of this. So it works CAN high and CAN low. When you send a 1 bit through the CAN, it pulls both the lines. That is, it will send. Let's say it sends. It will make the high as high and the low as low. That is, it will decrease the voltage in low and it will increase the voltage in high. And if it sends 0, it will do the opposite. So in both cases, it will reduce or increase the voltage in both the lanes. And this uses a concept called differential signal. So this is useful when there is electromagnetic induction. So these wires will rest at 2.5 voltage. That is the rest voltage. When there is no operation, it will be 2.5. So here we can see that 0 is sent. When 0 is sent, CAN low is decreased to 1.5 and CAN high is increased to 3.5. The difference between these volts is 2. So whatever happens on both the wires. Then when 1 comes up, when you send 1, the CAN low will become 2.5 and CAN low will become 2.5 and CAN high will become 3.5. So 2.5, it will go to the rest voltage. So let's say there's an electromagnetic induction and there is some interference. The thunder symbol is the interference. When that happens, both the lines will get affected. When both lines get affected by the same moment, the differential voltage is still the same. That is, you still have 3.6 minus 1.6. You still get the 2 volts. And so you don't infer the bit as 1 or 0. It will be inferred correctly. This is the property that makes it usable inside the car. And it also, since it runs on only two wires, it doesn't make a mess. So it is easy to connect components. And this follows a bus topology. So everything is connected to the main cable. So without CAN, you can see there is a lot of wires interconnecting. It'll be hard to maintain. With CANs, it is just 2 wires for each. So this is a CAN packet example. So how the packet will be. The first one is arbitration. So since this is a bus, follows a bus topology, the CAN message will be broadcasted. So let's say ECU A sends something to ECU B. Every ECU will be able to hear it, will be able to see it. So how will the B know, ECU B knows that the message is for ECU B? That is taken care by the arbitration ID. Arbitration ID is similar like a ECU identifier. So each ECU will be given an identifier, and when the it sees that identifier in the CAN bus, it will take the data, or else it will leave the data in the CAN bus. It will reject the data. And this arbitration ID is priority based. So the lower the number, the higher the priority. So airbag issue is critical, right? So when you crash, the airbag has to come fast. So airbag issues will be assigned a lower number. The next is for us, the next field of interest is control. In control, you have DLC 1023. That is the data length. How much data that is the packet contains. And then you have data. Data is the actual data. Then you have a CRC for integrity check. Then you have end of frame. And yeah, this is the CAN packet format. And you can only send 8 bytes of data in a single frame. If you want to send more than 8 bytes, there is another protocol called CAN-FD, and that will also allow only 64 bytes. If you want to send more than that, there are other protocols. So I'll show a demo of CAN injection. Since when they designed CAN network, they didn't care about security. And since it is on a bus, everyone can sniff the data, then there is no authentication. So anyone can inject the data or send malicious data or impersonate an ECU, and anyone can replay the attack since there is no timestamp or something. So anyone can replay as well. So the tool set that will be used is CAN utils. CAN utils have multiple tools. One is CAN dump, that is to see to sniff the data out of the canvas. You can see what message that goes in the canvas using CAN dump. CAN player is for replaying CAN logs. CAN send is to send a single frame. CAN gen is to generate random CAN traffic. CAN sniffer is similar to CAN dump. You can see the sniff the data out of canvas, but additionally you can see differences. That is what messages is different from the previous one. So there is something called ICSIM, which virtualizes the CAN network and gives you this the dashboard, virtualizes the dashboard, so you can play with it. So I'll take that up in the call next. So this is the GitHub link. Okay, 1 second. So there is CAN by default in the Linux. So you set up the virtual CAN interface by running these commands. This will load the virtual CAN interface and link it to a interface. And for this to run, the prerequisite is to install these packages. libstl is for the graphics that you get, that is the GUI, and CAN utils is for the to do CAN attacks. So when you install, you have to do first you have to run you have to set up the vCAN. That is, you need to get the virtual CAN interface, and the commands that we saw in the GitHub is placed in the shell script. You have a set up CAN. Okay, I've already done. So after you do this, you can check the interface and you will have a vCAN 0. And after you get this, you have to do a make to compile the C files to get the executable. I've already done it already. So when you want to start it, you have to do control. So you have two two executables. One is controls, one is ICSIM. ICSIM is the dashboard simulator. Controls is what you can do with the keyboard. So we'll first start the ICSIM. ICSIM and the interface that you have to, the virtual CAN interface that you have to do. You open up like this, and you have controls. Similarly, you do give the virtual CAN interface. Now, after it's opened, you can see that the speedometer is starting to run. So the controls are simple. You have to give up to increase the speedometer, and down to decrease or leave it to decrease it. And left is for left indicator, right is for right indicator. Right arrow. Okay, I don't know why that didn't work. And if you press both, you will have both indicators on. Now, to see what happens, you can do can sniffer, and to run the command, you have to give the virtual interface, virtual CAN interface. You can see all the data that is going on. So this also generates random CAN traffic in the backend. So now we can do, if you press C and enter, it will become colorized. So you can see what are changing. And if you do hash symbol and enter, it will do suppressing highlighting. That is, it will show only the ones that are coming up new. So now if I press up, you will be able to see something that is changing here. You can see here it is climbing up to, the values are climbing, which means that arbitration ID is what the dashboard issue is. So you can just send data to this arbitration ID, then you will be able to see the increase in speedometer. We can also dump this to a log, so you can do a replay attack. So -L can dump, -L is for outputting it to a log file. VCAN0 is the virtual CAN interface. So this is dump in this format. That is the CAN dump and the date today. So if you do, we'll do some action. So I'll increase the speedometer, and I will turn on the indicators here. Now if I give a Control C, and if I replay the CAN logs, -I is for the input CAN dump file. I can see the speedometer increasing. Now it's replay, then the indicator turning on. And this is the example for CAN injection attack. Go forward with the presentation now. We have one more demo at the end. So the way you can protect this is by having MAC. This property is called secure onboard communications. This is again a standard in cybersecurity now, in automotive security, that you can protect critical messages using this MAC. So to prevent replay attacks, you have a freshness value that is new every time. So someone doesn't replay the CAN message. Then you have a secret key in each ECU, which does the MAC calculation. So you open the MAC and the freshness value of the payload, and the receiver can again unpack it and verify it. And this is only needed for the critical messages, not every message. So if you do, since these are embedded devices, they can't run algorithms at a very high speed. They are very constrained. So when you start using this feature, enabling this feature for every message, then the load on the bus will get higher, and there will be latency issues. So it is only recommended to have this for critical messages. So next one is onboard diagnostics. So when you take the car to the service station, how will they tell that there is a problem? How will they find the problem? That is done through this onboard diagnostics. So this is the OBD port that you have in the car. This through which you can connect and get access to the canvas. Then you can sniff and do everything with the canvas, like what we did here now. So this will be placed below the steering wheel or the dashboard normally, but you can find it in your car. So this follows a protocol called UDS, and UDS Unified Diagnostic Service. This is standard for onboard diagnostics. So the commands that you can send in the canvas to get the diagnostic data is defined by the standard. And the protocol used is ISOTP. So with CAN, you can only send 8 bytes. But what if you want to send more than that? You use this ISOTP protocol, which is ISO transport protocol. This is similar to the TCP, which this basically does the flow control for you to send multiple messages and receive more messages than 8 bytes. So it will split it into frames and send it. And this is defined in the spec ISO 157652. And the format of ISOTP is this. So you first have the protocol control information, and you have the protocol data unit. PDU is the actual data that you want to send. PCI will contain the first 3 bits are arbitration ID. The next 3 bits are the data length. So how much length do you want to send in a single packet? So in a single packet, you can send only 8 with CAN, and with CAN-FD, I think you can send 64 bits, 64 bytes, sorry. And the flow control is done like this. So if you want to, sorry, the first byte is flow control, first nibble. So if you want to send only once a single packet, you send it with 0 as the first byte, first nibble. And if you want to send multiple messages, then you will use the first frame for sending the first actual frame, and then the consecutive frame for the next frames. So the first frame will have the nibble as 1, and then you have the total data length, that is how much you want to send the entire message, and the first byte will have the data length for the first frame. Then in the consecutive frames, you will have the first nibble as 02, and the second nibble as serial number, that is so that it can be reordered properly. And there is a flow control packet where this is for the receiver, like how many blocks they want to get, or how many milliseconds they have to send between the packets, between consecutive packets. And you can have 0 flow status is also there, where you can say 0, that is you can send it everything at once. Wait is and then you can abort the receiving information. So this is the Wikipedia for it. So you can see all the functions that can be done. The example is read diagnostic trouble codes. So whenever there's some problem happens in the car, it will log a DTC. And when you take the car to the service station, they'll first read the DTC to check if there is any problems logged, and they can get more information on it. ECU reset is to restart the device, and read data by identifier is like reading values from a variable. You will read the values from a non-volatile memory by using identifier. And routine control is used to perform some functions that you want to do. And this is a sample request and response of UDS. So when you send let's say you send as 10 is the data, the starting is the 10 for data. Here the first is the arbitration ID 6BD, what you see, and then 02 is the protocol information and the length, and then you have the function that you want to do, that is whether you want to do read by data by identifier or the flow control, the ECU reset. And then you send the data, the sub function, like it will be defined in the UD standard. So whenever you get a when you get a response, you first check if it's plus 40 of the service identifier. So let's say we received 50 here. This means it's 10 plus x 40. This means this is a successful response. If it's negative, you will get 7F, like the last one. And with negative response, you will get also some error codes with which you can see why the command failed. So you can get additional data. This is a sample flow where you want to send multiple, a big frame. And so first the client will send a single frame, and the first frame will be sent. Then the client has the flow control, that is the block size and the time, and whether you have to send or abort or wait. So when you do this, then all the consecutive frames will be sent at a time. So we'll have a demo on interacting with the UDS now. So there is some CTF called Black Harbor Security CTF, where this is for automotive security. All the channels you here you will see are mostly automotive security, and they provide they provide simulation as well. So you don't have to do anything. You just have to connect to their terminal and perform automotive hacking. So let's first try simulation win. So the challenge tells you to retrieve the win of the simulation using UDS. So we have to retrieve something called win from the car. So win, if you do a Google search on win is the vehicle identification number that is specific to each vehicle. So if you do a Googling of win UDS, and you should get the how you can read the win using the diagnostic protocol UDS. So you have to use the read data by identifier function. Inside that, you have to use the function subfunction F190. This will give you the win. It is a on-time byte of data. We'll try simulating this, performing this. So when you connect to their okay, on screen. When you connect to their server, you will get a tmux. You can open multiple terminals with control B and double quotes and control B and percentage, with which you can open multiple. So first, let's try doing CANDUP here. CANDUP, again, the interface you can check, it's vcan 0 here, and do a CANDUP vcan 0. So there is some data already going broadcasting in the CAN bus, and in their tutorial they would have given the arbitration ID, so you don't have to find the arbitration ID of the ECUs. And to send this, we have to send it through ISOTP protocol, and there is a command line utility called ISOTP for sending this. And the one that we saw was 22, which is read data by identifier, and the data F190 for getting the win number. You have to send it through ISOTP send, and you give the source ECU 7E0. This is already given by them, and the destination ECU as 78. And then you have to provide the interface. Along with it, you can give -P00, which is for padding. If the data bytes are less than 8, you can just pad it to 8. Okay, okay, let me do this once again. So here you can see we got some data. This is what we sent. That is 3 is the data length. 22 F190 is what we sent, and we got this packet. So if you see here, the first one is the first frame. So this is going to be a consecutive. This is going to use flow control, because since the data bytes are the length is 17, so you have to send it in multiple packets. So you can retrieve that at once using again a utility called ISOTP send. So we'll have the CAN dump running here, and I'll open ISOTP receive here. And again, you have to give the source as 7E0, destination as 7E8, and -P00 for padding, and -L is for the interface. If you do vcan 0, it will start listening in the canvas for that particular arbitration ID. We send it here. So now we got the entire bytes here. So if okay, we'll first analyze this response here. 62. So 22 is what we sent, plus 40 this is. So this is a successful response. And after the successful response, you will get the service identity and the sub function. You will get this here. And then after this is what the actual data. So if this is 17 byte data, and you can see in this CANDUMP here, when we tried it first, we only got till here. The reason that we didn't get the extra data is because we didn't send the flow control, that is the 300 frame. And ISOTP did it for us automatically, and so ISOTP receive as an abstraction here. And then you get the next frames, that is 2 is for the consecutive frame, and 1 is the serial number, and 2 is the serial number. So if we, this is actually the flag. If you do the, if you get the flag. This is how you can interact with ECU. There are multiple things you can do here. One is security access. So security access is again a way to, it's a way of access control here. So you can't let everyone get the same access. That is, everyone through onboard diagnosis, you can even reprogram the firmware. You can give your own firmware, and you can do a lot of dangerous things. So you can't give everyone the same access. You need to have some access control mechanism, and that is security access here. And security access normally uses the challenge response protocol. So and the identifier is 27. If you have time, you can try this, and at the end you will be able to do, I think here you will be able to do reverse engineering, and at the end you will be able to upload your own firmware and get a remote code execution. And this is a good playground for trying out automotive security. So we'll continue with the press slides. So there are multiple standards. There are multiple ISO standards here, and some software specific standards. That is, the software engineering specific standards are AUTOSAR and ASPICE. So AUTOSAR is a layered architecture similar to your OSI network layer. So this is a layered network architecture that governs how the software in the car will be. This has a specific purpose. So let's say, and the ECUs are microcontrollers, and when different microcontrollers are used, they need to be used differently. The way of handling their peripherals are going to be different. So the first layer that you see here is the microcontroller abstraction layer. This will be directly dependent on the microcontroller. So this will have the code to interact with the microcontroller. Then you have ECU abstraction layer. There are some things that can be specific to an ECU. That will be in the ECU abstraction layer. Services will be a normal one, like you have cryptographic services. The diagnostic service that we saw now will be in the services layer. Then you have the runtime environment. After this is the application layer, where people develop their own application, like the telltale signs that you see. Telltale signs that you see. And so the architecture is interesting because it provides a abstraction over at each level. So let's say you develop something at the services layer. Let's say you develop a cryptography service that can be reused across multiple microcontrollers because of this services layer. Since the handling of the microcontroller will be abstracted, you don't need to rewrite it. It's similar to how all the normal softwares are written. That is, like, we have a lot of abstraction whenever we write code. And it is good to learn this because every software that goes into the car will follow this architecture. So it will be helpful for you to reverse engineer as well. And then you have ASPICE. ASPICE is an automotive spice, which is targeted in the process on how you do the software engineering. That is, how you write code, how you test, how you design. So when you write a code, you have to attach every piece of it needs to have every piece of information. That is, the functional test reporting, the unit test that you do, the static code analysis, and design on how it works. This is automotive space. So every manufacturer that gets software or products from the suppliers will actually want this. If you don't have ASPICE, then they won't accept your software. So the next is the technologies driving cybersecurity in cars. So these are security modules that, so let's say we use symmetric algorithms. Symmetrical, how will you store the key? Because if the keys are if someone knows the keys, then they can do whatever they want, because symmetrical algorithms use only one key. And that is done by, and for that we have these specific modules. One is HSM, hardware security module, TPM, trusted platform module, TE, and trusted execution environment. And TPM is mostly to a host. It is attached to a host, not to an embedded device. So in your laptop or your PC, you can see TPM there. TE is for execution of sensitive applications like the payment application. Only the trusted applications can execute in an environment, and the non-trusted one will come as a separate one. So you have non-trusted world and the trusted world. HSM is the most commonly used in automotive with this hardware security model. The main purpose of this is to store keys securely. So whenever you want to do some operation, you have to ask the HSM to do the operation for you, because you won't have the key. HSM will only have the key. And in that way, the keys are not given out, and keys are securely stored. And there are some other security properties as well that you can enforce here. So here is an example for an HSM. So these are some microcontrollers that are inexpensive and supports HSM. You have Infineon Travio 2 and Infineon Oryx. Oryx is the high-end chip that you get. So when you use high-end chips in your car, the cost of the car obviously goes up. So only in high-end cars you can see this chip. So some other security measures that you can enforce are secure boot. Secure boot, again, this also you have it in Windows. That is, it checks if the software is authentic, whatever the software that helps you boot up the first stage software. So this is again split into two components. One is the root of trust and chain of trust. Root of trust is what that remains unchangeable. So if root of trust is compromised, the entire system is compromised. That is the ideology. And here we can use asymmetric signature schemes. So the software will be like this. It won't be just data. You'll have a signature added to it as well, the signature of the data. So an example here is the root of trust is the public key, which will be which can be flashed only once. An example. So public key cannot change. So any software that the OEM gives you will have their own signature, and the signature will be used by their private key, and the respective public key will be in the one-time programmable area. So whenever you start when you boot up process, you check if the boot software is correct by taking the public key from the one-time programmable area and doing a signature verification. Then you do the chain of trust is then you do the second bootloader. Since you can't, the size of the application might be bigger, so you can split it into chunks and verify it stage by stage. That is secure boot. The next one is secure over-the-air update. Over-the-air update is very critical because the data comes from the external, so you need to have it secured. And again, the mechanism that you can do is signature scheme. So instead of just the data, you send the signature as well, and the public key will be fused in will be placed in a one-time programmable area. So whenever you receive that bit, you can verify it using the public key, and if it's verified, you can go for writing it to the memory, or you can just ignore it. Then secure storage. This is the key storage part where you want to store the keys securely. That is, no one can read the keys. No one should be able to keys from, even if you have only one core and HSM is in the core, in the same core as the application core, you should be able to do a logical division there. And then we have secure lifecycle. So when you are in the development phase, you would be able to debug the software. This is done by the strategy called JTAG, Joint Test Action Group. This is a pin that you can see here, the 10 pin it will be. You can connect a debugger to this 10 pin and you can debug the software. And when you go to production, you can't have the debug enabled. So you disable this JTAG feature, or you secure it with a password. So whenever someone wants to debug the software, they have to unlock it using a password and then go for debugging. So some other attacks that can be done on the automotive side is side channel. This is you extract secrets by observing unintended information. So the microcontroller leaks some data that can be used for this. So an example is time analysis, power analysis. So here is an example source pseudocode. Here it is possible to do time analysis to get the original password. So let's say original password is hidden somewhere, and this is the password check function that takes your user input and does the validation. So first it checks if the length is not equal or not equal. If it's not equal, it returns a false immediately. So let's say so here the password length is 8. If I enter just one letter, the code will return back immediately. If I enter 2 letters, the function will return immediately false. The program will get executed very fast. And so with this, the first step, you can decide find the length of the password by giving different inputs and measuring the time. So if you give 8 letters, it will pass this check and it will go to the for loop. So there will be some extra time taken. So you can find that the length of the password is 8. And then you can go forward with getting the correct value. So if you see the for loop here, it will check if the first character is the original password's character. And if it's not, it returns false immediately. So again, you can brute force character by character and get the password. So if you give A and it returns immediately, but if you give P, it will take some time because it has to check the next letter as well. So that will take some time. By using time as a measure, you can find the password here. This is an example of side channel. There are other examples as well where you can do power analysis. That is the power taken by something, power taken for compute. So you can see what the data is. The next is fault injection, where you induce faults internally. So a false meaning you can do a voltage fluctuation. You can see by giving a high voltage that the board cannot handle, and you can see if the board what happens. Sometimes the security checks get skipped. So the system goes to an undefined behavior when you do voltage fluctuation, when you do fault injection attacks. So that is some attack. There are some successful cases as well for this. So future, if you see future, we have so you can see that the automotive security is based on cryptography mainly. So everywhere you can see the use of symmetric, asymmetric algorithms. So cryptography is the main part. What if it gets broken? So with the so these cryptography are based on something called hard problem. Hard problems you can do the compute at one forward direction easily, but when you do an inversion, it will be hard. So let's take RSA as the example here. So this is the example algorithm. This is the algorithm of RSA, but you don't need to mind this. So only line number 3 is important for us. So the line number 3 is n equal to p into q. P and q are the private part of RSA. That is, it constitutes the private key. If you have p and q, you can get the private key. You can make your own private. You can force. You can get the private key, and n is the public part. N will be known by everyone since it's public part. If you can divide n to p and q, you can get the private key. And another thing is p and q are prime numbers here. So it looks easier, but it's very hard to do. This problem is called integer factorization, where you take a number and you try to find the prime factors of it. So when you get the 2 prime factors, that means those are p and q. But there is no proper algorithm to compute the prime factorization in a feasible time. There is no other choice but to brute force. So, and n is not small here, it will be 256 bytes. So when you want to do a brute force of 256 bytes is 2 power 256. That will take very long number of years to compute. So this works now is because of the machines that we have are not able to compute faster. But with the advent of quantum machines, you can break it. You can do brute force on it, since the quantum machines are much more advanced. Algorithms will be converted to or migrated to algorithms called post-quantum cryptography. So there are some algorithms that are released for post-quantum. So they are much more advanced, and they depend on something called lattice-based. They are much more and very hard to break. So uh, in the future, all the algorithms will be migrated to post-quantum cryptography. Yeah, I think that's it from my side. If you have any questions, you can ask. So yes, I'll send the link to the Google Sheets. So correct, you can't pass scan log without DBC file. DBC file. So to reverse engineer to find the arbitration ID, but not always that easy, because in a real car you will have much more data going on, so it will be very hard to reverse engineer. But there are some people, the security researchers uh, have made these can reverse engineered and have open sourced the CAN DBC files, the CAN database that will have the mapping with the arbitration ID and the signal. So you can use that for parsing the CAN logs, or you would have to reverse engineer it by yourself. It is very hard. Yes. Any other question that you have? I'm not sure about. Yeah, I'm not sure about the electric scooters. They might use HSM for security purpose. Like it's still automotive, and automotive you still have software updates there. It will be better if they use HSM. Any other questions? Uh, they can, but because it is again it is constrained. You can't run high software, a very big software there. But yeah, it can detect malware, automotive based malware. Uh, okay, that's a good question that I don't have an answer to, because I also just started my career in automotive cybersecurity. But there are some CTF that happen, like the one that I showed. Automotive security is slowly picking up, and it is becoming very critical now. It is growing very fast now, so it's better to learn something. So there will be CTF getting connected, and you can become expert at the ISO standards if you want. You can get ISO certified. Those are some certifications that you could do. Yes, you can enter. Since this is basically hardwares, EC students are perfect to enter into automobile engineering. And I know a lot of people where I work. I know a lot of people who are mostly ECE engineers. Like CS engineers are very less in number here. Any other questions here? Uh, like automotive industry is just picking up, but you still have the penetration testing team here. Since you need to test the in-house products that you develop, then you have software engineers for developing the software. You have hardware engineers. You basically have all sorts of role here. The most in demand, I think cybersecurity is the most in demand role now in automotive industry. Mostly the penetration testing side. Okay. Thank you for spending your time here. Yes. Do you have any questions, Thomas?
No, bro, it is by mistake.
Yeah, no problem. Okay, we can wrap the session then. Thank you for spending your time here.